Welcome back. Well, we're starting a new unit on solutions, and our first section in this unit is molarity. So this is 7.1 molarity, and this can be found in chapter 16 of your book. Before we start talking about molarity, let's just review about precipitation reactions. Okay, so we have what type of reaction here? All right, if you said double replacement, then you're correct. And remember, to get the products of a double replacement reaction, we have to combine the inside and the outside. All right, so remember inside, outside. And also remember that just because this has a 2 subscript here does not mean that over here in the products that it will have a 2 subscript. And this is, remember, a polyatomic ion, so we don't change this 3. So let's put the inside together, Ca and NO3, okay? And just because there's no subscript here does not mean that there will not be a subscript here. What we have to do when we put these together is we have to look at the charges. Remember, we have to check the charges. All right, so calcium has got a +2 charge and NO3 is a -1 charge. Well, this doesn't make 0, so we have to swap and drop. So I'm going to have to add parentheses and add a 2 there. Okay. Silver is a +1, chlorine's a -1. So those do make 0. So AgCO, we just smash those together, and that is the formula. All right, so here is the correct products and formula for this reaction. Okay, now when we are deciding about a precipitate, remember we use the solubility chart that's in our reference materials, and we have to look at these ions. Okay, so we're going to try to find calcium on this ion list. And it's not always soluble. There's no calcium here, no calcium here. Calcium's here, but it's an exception, okay? And no calcium here. So now we're going to look for NO3. Always soluble. NO3 is right here. So this tells us that this is soluble. So what that means, it's going to dissolve in water. So now let's look for AgCO. Well, no Ag here, no Ag here. So Cl is not an alkaline metal. Okay, so it's not there. There's Cl right there. All right, so it is soluble except with silver. Okay, so this is going to be our precipitate, the AgCl. The AgCl is not going to be soluble in water, so it's going to precipitate out as a solid. Okay, so let's remember how to use this. Well, molarity is a term that means the number of moles of solute that are dissolved per liter of water, or how much solute is dissolved in the solvent. It is a numerical value that tells us the concentration of a material that is dissolved in water. So looking back at this, AgCl is not soluble in water, so we would not be able to tell the molarity of the AgCl dissolved because it's a solid. However, the calcium nitrate, it does dissolve in water. So we can look at how many moles of the calcium nitrate is dissolved in a certain amount of water or liquid and determine a numerical value for the concentration, how much. And concentration is in molarity. That's a capital M is the variable for that. And it's the formula is the number of moles of solute divided by the liters of solvent. Okay. And we can use this nifty little triangle here to help us figure out different values. Like, say, if we wanted to know how many moles and we had the molarity in the liters. So I'm going to use this little square, but what you would do with your finger is cover up the answer that you want to solve for. So we're solving for moles. So it's molarity times liters. When they're next to each other, it's multiplying. So molarity times liters is moles. And that is a very, very common equation. A lot of problems will ask how many moles or how many grams of this are dissolved or need to be dissolved. So this is a very common equation to solve for moles. Now remember, it's molarity times liters. Okay. Another one, like if you wanted to solve for liters, it's moles. And when they're on top of each other, like with this line, it's moles divided by molarity. And if I was solving for molarity, just like this one, it's moles over liters, moles over liters. So if you put the variables in a triangle like this and then draw a T here, cover up the one you want to solve for, and it tells you. Okay. Now, when chemists express a concentration, it looks like this. So, like, say, for example, if we want to draw 14 grams, then we would do this, right? So for a solution, when we're writing the concentration, it's 2.3 and then a capital M after that. Or an alternative way to do that is to put it in squared brackets. And when you put a number in squared brackets, it's understood that that is the concentration in molarity. And you're going to see this a lot. Okay. All right. So here's some examples. The average concentration of ocean water is 0.60 molar. Okay. And that's how you read that, is 0.60 molar. How many grams? Okay. So how many grams? And here is a given, circling that, of salt, NaCl, are in a toy bucket containing 435 milliliters of ocean water. All right, so here it is. How many grams? This is very common. Now we need to solve for moles, because remember, once we have moles, we can use the mole map to solve for grams. So moles is equal to molarity times liters. All right, so take your molarity, 0.60 times liters. All right, so this is in milliliters. So liters, we divide by 1,000. So it's going to be 0.435 to convert that over to liters. Okay, and grab your calculator. 0.60 times 0.435. That's going to be 0.261. Now remember, this is moles. Moles. Now we need to convert this to grams. So put it over 1. And what unit do I want to get rid of? That would be moles. So put it over here to cross cancel. What conversion factor can I put here that gets me closer to what I want? Well, we know we can go straight from moles to grams. All right, and this unit, grams per mole, is the molar mass of sodium chloride. So 1 mole is, and let's look up sodium and chlorine. Chlorine's 35.45. Sodium is 22.99. Adding those together, we get 58.44. Moles cancels moles. We're left with grams. So it's 0.261 times 58.44. That's going to be 15.25284. All right, counting sig figs, we see we have, let's see, 2 sig figs here, 3 here. So we're going to go for 2, our least amount. So here's 1, 2. So we look at the next one for rounding. 2 does not round that. So it's 15 grams of salt. 15 grams of salt. All right. What volume of a 3 molar hydrochloric acid solution should a chemist dispense to obtain 0.25 moles of hydrochloric acid? All right. So what volume? That's what we're looking for. Here's a given, and here's a given. All right, so if we're looking for volume, I'm just going to redraw this. So it's moles, molarity, liters. So what volume? Let's cover up this. It's going to be moles divided by molarity. It's going to give me liters. So 0.25 moles divided by 3.0 molar. Okay, and that's going to give me liters. All right, so 0.25 divided by 3, 0.083 repeating, and we need 2 sig figs here, 2 sig figs here, so we need 2 sig figs. All right, so leading zeros never count. 1, 2, the next is a 3. The 3 is not going to round, so let's count 1, 2. The 3 is not going to round, so our answer is 0.083 liters. All right, very simple calculations here. All right, so the concentration of ions in solution. So let's look at this. So here we have, let's just say we have 1 mole, okay, because there's no number here, so we assume it's 1 mole of aluminum sulfate. Is that sulfate? Let's make sure. So let's check our SO3 polyatomic ions. It's sulfite. Okay, so be very careful with that because sulfate is SO4. You see right down here? SO4. Sulfite is SO3. Now they both have a -2 charge, but be very careful with that. Okay, sulfite, just like nitrate and nitrite. And there's also a phosphate and a phosphite, but phosphite's not listed here. Okay, phosphite would be PO3. Same charge though. All right, so this is aluminum sulfite. All right, so we have 1 mole of aluminum sulfite, but what makes up aluminum sulfite? Aluminum sulfite is made of 2 moles of aluminum and 3 moles of sulfite. So the law of molar ratio says that for whatever concentration we have of aluminum sulfite, when this dissolves, we're going to get 2 times that concentration of aluminum ions and 3 times the concentration of the sulfite ions. So if we had a 3 molar solution of aluminum sulfite, 3 molar, when this dissolves in water and it breaks up into its ions, okay, we're going to have 2 times that amount. So we're going to have a 6.0 molar concentration of aluminum ions and 3 times the amount of the sulfite ion. So 3 times 3 is 9 molar concentration. Okay, and that's the law of molar ratios. Okay, so when you're doing some of these problems, they're going to ask you that question. And because it's a 1 to 2 to 3 ratio in this equation, then we have to make sure we double that concentration for the aluminum ions when it dissolves, and then triple for the sulfite. And that's true of any ratio of the soluble compound. Okay, mixing concentrations. So what we're doing here is we're going to mix two solutions together and assume that no reaction is going to occur. And then we need to get the concentrations of the ions that are in the mixture. So it tells us here that we have 15 milliliters of a 3 molar HCl, and that's going to be added to 10 milliliters of a 2 molar calcium chloride solution. Calculate the concentration of each ion in the solution and assume no reaction occurs. All right, so let's look at this. We have HCl that we're adding to CaCl2, okay? And when we do this, we're going to get hydrogen ions. We're going to get chlorine ions. Let me spread these out a little. Actually, I don't need to. We're going to get calcium ions, and we're going to get chloride ions. Okay, so this is the net ionic equation. These are all going to be dissolved in the solution. So we want to know how many moles, what is the concentration, what's the molarity of each one of these ions. All right, so hydrochloric acid is a 1-to-1, okay? And so when it dissolves, it's 1-to-1. So if we look at the hydrochloric acid, we see here that we have a 3 molar solution. Okay, so this is going to be 3 molar, and this is going to be 3 molar. Okay, but we're adding it to this solution. So where it's 3 molar here, it can't be 3 molar here because we're increasing the solution by 10 milliliters. So this is going to be 15 milliliters plus 10 milliliters. So this is going to be 25 milliliters total. So what I want to do is I want to find the number of moles of hydrogen and chlorine that are going to be in the solution and divide this number of moles by the new molarity. The new volume. So in our concentration here, 3 molar, we want to find the moles of hydrogen. So that's going to be molarity, which is 3 times the number of liters. So that's going to be 0.015. And that's going to give us the number of moles of chlorine as well, because it's a 1-to-1 ratio. All right, so let's see here. 3.0 times 0.015. That's going to be 0.45. This is 0.045 moles. Okay, same here, 0.045 moles. Okay, now let's look at the calcium. The calcium was 2 molar, 10 milliliters. So if I want the moles of calcium, I'm going to take 2.0 molar times 0.010 liters. Okay, and so let's look at that. 2.0 times 0.010, 0.02 moles. Okay, now because we get 2 moles of this per 1 mole of calcium chloride. This isn't the 2 molar. Now this is going to be 4 molar. So this is going to be 4 molar, okay, times 0.010 to give us the number of moles. So it's going to be double. So just to verify, 4.0 times 0.010, and we get 0.04. So you see it is double, 0.04 moles. Okay. All right. And so this is, now we need to calculate the new molarity or the new concentration. So we have a new volume. Remember, our new volume is 25 milliliters. Okay, or that's equivalent to 0.025 liters. So we have moles, we have liters. So now we can calculate the new concentrations of each one of these ions. So the hydrogen is 0.045 divided by 0.025. Okay, so that's going to be 1.8 molar. Okay, and then let's do the calcium next because it's a cation. Okay, so 0.02 divided by 0.025, that's going to be 0.8 molar. And now the chlorine. Well, the chlorine, we have this many moles plus this many moles. So 0.045 plus 0.04, we have 0.085 moles. Now divided by 0.025 liters, that's going to give 3.4 molar solution of calcium ions. All right, so that's how you do that. Just remember that now in solutions, we're talking sometimes about mixing this volume with this volume. So we have a new volume, okay? We have a new volume, and we have to, when we're calculating this, we have to add these volumes together and then go from there. Okay, so it's an additive volume when you're mixing different solutions now. All right, dilutions. So there's also a scenario where we're given a concentration in some of these problems that we're going to do, and then we're going to add more solvent or more of the liquid part. And so what this does in the solution is it increases the volume, but the solute stays the same. So this means that it's going to be diluted. And this same kind of thing happens like when you get your Sonic drink. You know, you have your ice and, you know, you get the big, you know, Route 44. And so throughout the day, I mean, you just don't drink, you know, chug-a-lug the whole thing. So by the time you get to the end, some of that ice is melted. And so it dilutes the syrup or the concentration of the sugar or the flavor that's in there. So it's, quote, watered down. And so that's actually what a dilution is. And there's a formula for calculating that. And it's M1V1 is equal to M2V2. And we've seen these ones and twos before, and these are before and after situations or values. So let's say an example problem that you might see says that a chemistry student needs 25.5 milliliters of a 2.3 molar solution of nitric acid for an experiment. When they got to the lab, the nitric acid bottle says 3.0 molar solution on it. How can that student dilute the original solution to obtain the working solution that's needed for the lab? Okay, so the original solution is 3.0, and then the working solution for the lab, it needs to be 2.3. So it needs to be a lower concentration. So what we have to do is we have to add some water to this known concentration right here, 3.0, to dilute it to get it down to 2.3. So when you're diluting, you only water it down. We can only decrease the concentration of the solution. We can never increase it. Well, we can, but the way that you would increase a solution is you would have to either evaporate or distill some of the water off. And in a lab situation, you can never I mean, we can calculate how much we need to distill off, but when you're distilling, you can never stop at that exact point. So you're going to have to over concentrate it, distill off too much water, and then add a very known amount of water back in. So those kind of problems are a little bit harder to calculate, and it's actually harder to do. So this is why most of the problems that you see, you're going to have a lower concentration on the M2. Okay. All right. So let's go ahead and dissect this using glues. Okay. So we're going to circle our givens. Okay. Here's our givens. We're going to label this. So a chemistry student needs 25.5 milliliters. So that's going to be our V2. And we need 2.3 molar. So that's going to be an M2. And we're starting with M1. We're starting with a 3.0 molar solution. Okay, so how can they dilute the original to obtain a working solution? So we're going to be looking for a V1. Okay, we're going to be looking for a V1. So M1 V1 is equal to M2, V2. Okay, so I'm going to rearrange this to solve for V1. So I need to divide both sides by M1, and that's going to give me the volume. Okay, so let's start plugging in. So M2 is going to be 3.0 molar over, V2. I'm sorry, let's do V2. And this has to be in liters now, so we're going to have to convert that to 0.0255. Okay, over the original volume. Wait, M2. I put in the wrong number. Oops, let's go back. This should be M2. See, M2 2.3. Okay, and how much do I need? 3.0 to get it to 3.0. Molar. All right, so let's go ahead and plug these numbers in. .3 times 0.0255. Oops, I had a wrong button. All right. 2.3 times 0.0255, 3.0 on bottom. Okay, so I get 0.01955. All right. So, and this is in liters. So if we want to, that's hard when you're actually in the lab and you're measuring. We measure in milliliters instead of liters. So we want to convert this back down to milliliters. So move the decimal place 3 times this way. So we get 19.55 milliliters. Okay. And then we have 2 sig figs here. So this is 2 sig figs. So we're going to need 19.6 milliliters. Okay. Is our answer. All right. So we want 25.5 milliliters total. So we're going to use 19 milliliters of this 3 molar solution and the rest water. Okay. So we can calculate now. We can go ahead and plug these in and check to see if we got the right answer. So the way we do that is we plug it back into the original equation. Okay, so M1 is 3.0. Okay, and then 19.6. And that should equal 25.5 times 2.3. 0.025, okay, and 0.0196. So when we multiply these, they should be equal. 3.0 times 0.0196 is equal to 0.0588. And let's check to see if that is correct. 0.025 times 2.3, and I get 0.0575. Okay, so 2 sig figs, it's about correct. You know, we have our rounding errors, so that's pretty much correct. Okay, so we need 19.6 milliliters of the 3.0 solution. So 19.6 milliliters of the 3.0 molar solution, but it needs to be a total of 25.5 milliliters. So the rest of this we're going to have as water. So let's go ahead and 25.5 minus the 19.6. Okay, so that's going to be 5.9 milliliters of water. Okay, so we're going to need, to make this working solution, we're going to need 19.6 milliliters of nitric acid and 5.9 milliliters of water to get a total volume of 25.5 milliliters. So we're going to have to take and mix these together, acid and water. Now, remember, when you're mixing acid and water, always remember A&W root beer, acid into the water. So we're going to take the 5.9 milliliters of water, and we're going to add the acid to it. And then our last topic that we're going to discuss is conductivity. So when an electric charge is carried through a solution of liquid, then it's said that the liquid conducts electricity. So the electrons move through this solution, and it's carried by the ions that are in the solution. So the solution that's conducting electricity is called an electrolyte. So a solution that conducts electricity is called an electrolyte. And you've heard that word electrolyte before, because drinks like Gatorade contain ions, or they contain these like calcium, magnesium, these ions, so that it helps the electrical functions, the electricity that your body normally uses to function. It allows it to go through your body. So if it does not conduct electricity, then it's a non-electrolyte. Okay, and the more ions that are present in solution, the greater the conductivity. So it would seem to reason that the less ions that are in solution, the less it conducts electricity, the more it's a non-electrolyte. So pure distilled water does not conduct electricity because it does not have ions in it. There's no ions in pure distilled water. You know, we're always told not to have any electrical devices around, you know, the bathtub or the sink, because if you knock them in, then that electricity, and they're plugged in, that electricity can go through the water. And then if you are in the water or you touch the water, then you can get shocked and possibly die. But I want to caution you, even the distilled water quote that you get from the grocery store, this is not lab grade pure distilled water. That there's some still ions present in that. So don't test that hypothesis at home. Okay, there's ways that you can test for conductivity, and I'll show you in a demonstration in class. I have a conductivity meter, and I'll show you some of these things. So there are still ions present, and it will conduct electricity from the distilled water that you buy at the store. Okay, so here's some bullet points I want to go over. Electric current is carried through a solution by ions, and the more ions, the higher the solution's conductivity. Okay, and we're going to see that in a class demonstration. Soluble salts dissolve in water to make aqueous solutions with high ion concentrations and consequently high conductivity. Low soluble salts form solutions with low ion concentrations and therefore have low conductivity. Molecular compounds like sugar do not form ions in aqueous solutions. So for their solutions, they do not conduct electricity. And this would be like sugar, water. Sugar does dissolve in water, but it's just big crystals dissolving down to molecules. The molecules don't actually split up into separate ions. So it does not conduct. Sugar water does not conduct electricity. Strong bases and strong acids ionize completely, which means that they split apart 100% in solution. So strong acids and strong bases are strong electrolytes, and weak acids and weak bases only ionize slightly, so they'll make weak electrolytes. All right, so that's it. Thank you for watching. Make sure you slap that like button right across the face. Make sure you like and subscribe and leave a comment.